Okay. Welcome everybody. I can see that a lot of you are going to are connected yet, are going to be connected. So welcome and thank you for joining our first virtual meeting about the INNO-VEG project. My name is Jean-Pierre Cour from Arvalis in France, and I'm going to introduce this meeting by first of all, give you some general information about how the meeting will be conducted. So the first thing, all microphone except the microphone of the presenter, of course, will be disconnected. So you will be allowed to ask some question, but please use the question box on the dashboard you probably see somewhere in your screen. We will have during the meeting 2 question sessions to answer your question. And if we don't have enough time to answer all the questions, we will send by email an answer during the next few days to be sure that everybody will have an answer to its question. So our meeting will last approximately 1 hour. We'll try not to be too long. And one last thing, the meeting will be recorded, and it will be made available on the website of the project during the next week, I think. And we will also made available the slides. All the slides you will see today will be shared on the project website. Next slide, please. So the agenda of our meeting is on the screen. First of all, you will have an introduction presenting the INNO-VEG project by Lizzie Sagu from EDAS, and then 2 general presentation on the sensors we use in the project by Gis van Deel from INNO-VEG, and a presentation of how we calculate the vegetation indices we would like to study in our project by Hans Mulgray from Delphy. I will take the microphone again to show you the first result of our work on the comparison of the vegetation indices calculated by various sensors we use in the project. And the meeting will be concluded by Lizzie again to give you some information of what we will do during the last part of our project. So I give the microphone to Lizzie to start with the introduction. Thank you.
Perfect. Thank you, Jean-Pierre, and good afternoon, everyone, from a very wet and windy afternoon here in the UK. And my name's Lizzie Sagu, and I'm a soil scientist at EDAS, and I lead this INNO-VEG project. So just to start us off this afternoon, I want to give you a bit of background about the project and what we're trying to do. Next slide, please. The INNO-VEG project is an EU Interrreg2Seas funded project. The partners are EDAS in the UK, Arvalis in France, INNO-VEG in Belgium, and Delphy in the Netherlands. We started the project in 2018 and we'll finish in 2022. So we're about halfway through at the moment. Next slide. The overall objective of the project is to increase the speed and uptake of innovation in the field vegetable and potato sectors. The project aims to do this by evaluating the suitability of using crop sensing data to carry out measurements in the field experiments, and by then defining a new approach for delivering research experiments in these sectors. Next slide. So across the project, we're looking at 7 crop groups. And that includes alliums, so we've got leeks and onions, brassicas, cauliflowers, sprouts and cabbage, leafy salad, lettuce and spinach, vining peas, courgettes and potatoes. So you can see that we've selected a wide range of different crop types with quite different growth patterns, and that is deliberate because we wanted to see how well crop sensing data correlated with yields for a range of different crop types. Next slide, please. So in terms of the project experimental work and what we've been doing, last year in 2019, we carried out a programme of 47 small plot field experiments across the UK, France, Belgium and the Netherlands. When I say small plot experiments, this is the sort of scale that we normally work on when we do experiments on these crops. The actual plot size will depend on the crop, but might be as small as 1 bed wide by a couple of meters long. We typically use small plots just because it's very labour intensive to hand harvest some of these crops from larger areas. In our INNO-VEG small plot experiments last year, we selected and applied different treatments to the plots with the aim of trying to create a yield difference in the crop. We then used crop sensors to collect crop reflectance data from the plots during the growing season, and at harvest we measured total and marketable yield. And we've used the crop reflectance data to calculate a range of different vegetation indices, which Hans will describe in his presentation. And we then correlated these vegetation indices against crop yield. A key advantage of using crop sensing data to assess experiments is that it's relatively quick and easy to use drone-mounted sensors to measure crop reflectance from larger whole field areas. And this allows us to upscale from small plot to the field scale. And this year, in 2020, we've set up 14 larger field scale experiments. Here, the treatments have been applied to larger areas, often working with the host farmer and using farm machinery to apply the treatments. We've mostly used drone-mounted sensors to collect crop reflectance data from the fields, and we're currently using spatial statistics to analyse this data. So in this webinar today, we're going to focus on the work we've done to assess the different vegetation indices and compare data from the different sensors. We hope to hold either another meeting or webinar, COVID permitted, later in the project to present a summary of data from the actual field experiments. So I'd now like to pass over to Guys from Agro, who will talk to you about the different sensor types. Guys, over to you.
Hello, everyone. I am Guys, and I am a researcher, precision agriculture at INNO-VEG in Belgium. I'm going to give a quick introduction to the different sensors used by the partners in the INNO-VEG project, because every sensor has its advantage or disadvantage, and it was also important for us to look how comparable different sensors are. First of all, it is important to make a distinction between the sensor types. We can do this by looking at the spectral resolution. There are multispectral and hyperspectral sensors. A multispectral sensor will measure a limited number of specific bands in the light spectrum. There are, for example, 5 or maybe 10 bands, but however, a hyperspectral sensor will, within a certain range, give a complete overview of the spectrum. That's what you see on the lowest paragraph. So you have the complete overview of the spectrum. For example, 1 band for each nanometer in the spectrum. So at a hyperspectral sensor, there are usually more than 100 bands. There are also other possibilities, such as RGB pictures, thermal sensor, LiDAR. But in the INNO-VEG project, we focus mainly on the multi and hyperspectral images. Another way to make a distinction is based on the light source. There are active sensors with their own light source, but also passive sensors, which work with sunlight. With these passive sensors, it's important to measure the variations in sunlight during the measurement, because if the sunlight varies, the sensor will also measure another value. Another way of classifying sensors is according to the platform. There are handheld sensors, tractor-mounted sensors, and drone-mounted sensors. Satellite images may also be mentioned as a possible data source, but we do not use these in the project. The handheld sensors are operated manually in the field. The advantages are that you can use them in different experimental designs, and we can take multispectral but also hyperspectral images. The disadvantages are that it's labor-intensive measurements. It's difficult to carry out in large plots because the sensor have a limited field of view, so it's harder to take a representative measurements of a large area. An example is the FieldSpec Handheld 2, which is used by ADAS in their small plot experiments in 2019. It's a hyperspectral sensor which records reflectance values every 1 nanometer. It's important that calibrations are carried out regularly using a wide reference disk. It's to cooperate with the changing sunlight. Second possibility are sensors that are mounted on tractors or maybe spray booms or even specially designed carrier systems. The advantages are that we can have faster data collection than with manual measurements. There is also a possibility to do the data collection more automatically. Maybe sometimes it's a multi-sensor platform, so we can also attach heavy or new sensors like LiDAR or thermal cameras. Some of these sensors are hard to install on, for example, a drone, and these specially designed carrier systems can also have heavy sensors. The disadvantages are that you need tram lines, and because of these tram lines, the plots are limited in dimensions. An example of a tractor-mounted sensor used in the project is the Delphy sensor, which is developed by Arvalis. They developed a special boom sensor, which can make semi-automatic measurements using RTK GPS. The sensor boom is equipped with a hyperspectral sensor because Arvalis also plans their plots with RTK GPS, and they store these locations. They can quickly and efficiently carry out their measurements in the fields with many plots. Another tractor-mounted sensor is the Spectracam, which is used by Delphy. This sensor was designed to be tractor-mounted, but Delphy developed a special carrier to use the sensor in field trails. To make the sensor measurements more efficient, they equipped the carrier with an RTK GPS system, and it's a multispectral camera with an active light source. The third and last type of sensor we used in the project are the drone-mounted sensors. These are mostly multispectral sensors. I say mostly because the hyperspectral sensor is also possible, but at the moment, most commercial services in agriculture use multispectral sensors on their drones, and we also do that in the project. The advantages are that you can have a faster data collection, and it's also possible for large plot field experiments. The drones are easy to transport to different fields, but the disadvantages are that you need trained and skilled drone pilots, and there are a lot of restrictions in the drone legislation. The first sensor used in the project is the MicaSense Red Edge 3, which is used by ADAS in their 2020 field scale experiments. It's a multispectral camera with 5 bands. With this camera, we'll fly over the field with a drone in a certain pre-programmed order, and we collect a lot of pictures. And these pictures are stitched together to one big picture, and you can see an example of such a picture at the slide. The MicaSense Red Edge MX plus Blue is used by Inagro. So the blue is an expansion kit to the MicaSense Red Edge, which is similar to the one used by ADAS. The blue sensor gives 5 extra bands. So in total, you have 10 bands available with the sensor. So you can calculate more indexes. A last drone-mounted sensor used in the project is the DJI P4 Multispectral, which is used by Arvalis. It is an RTK drone with 5 multispectral bands and also an RGB camera. One advantage of this drone is that it's equipped from the factory with the multispectral camera. This way, you avoid problems installing a sensor on a drone, which often gives problems for communication between the drone and the sensor. With all these sensors, we can collect spectral data, and we use this data to calculate indexes. Now, Hans Maugré will give you more information about these indexes.
Okay, thank you, Gies, for the explanation about the sensors. My name is Hans Maugré, and I'm a consultant at herbal farming for Delphy in the Netherlands, especially in the southwest of the Netherlands. And my specialization is precision farming. I will talk in the next couple of slides about vegetation indices. And before that, we really have to know what we measure with the sensors we used. So one part we used is the reflectance of the incoming light from, for example, the sun or an active light source on some of the sensors. You measure the reflectance of the visual light and also on the near infrared light. So the visual light, you have a blue band, a green, and a red. And every plant gives a different reflection of those different light sources. So part of it will be reflected, a part of it will be absorbed by the plant, and some of it will be transmitted. As you can see, a healthy plant, for example, will reflect a different amount of visible light and a different amount of near infrared light than a stressed or unhealthy plant. So that's what we measure. We just measure the amount of reflectance of a plant. With those reflectance, we will use this reflectance for calculating a vegetation index. And a vegetation index is a single number, and it's calculated with two or more different reflectance bands. Can be the blue bands, as you can see, the green, the red of the near infrared. A lot of different vegetations have been developed last years, and we choose 7 different vegetation indices. And as you can see, every sensor uses a different wavelength for each band. So this is, for example, the Spectracam with the green, the red edge, and the near infrared. So every sensor can just have a slightly different wavelength which it measures. The 7 indices we measured, it's based on the experience of the project partners and also on the research which has been done in the last years. And one of the most common one is the NDVI, the Normalized Difference Vegetation Index. The second we used was the MCARI2, Modified Chlorophyll Absorption Ratio Index 2, the Chlorophyll Green Index, the Chlorophyll Index Red Edge, the NDRE, Normalized Difference Red Edge, the REIP, the Red Edge Inflection Point, and at last the MTCI, the Maris Terrestrial Chlorophyll Index. it's mostly based, our choice is mostly based about the experience of the project partners. And the NDVI, I think most of you have already heard about it. It's a very standard index, which is most used in the world, especially for drone images, for satellite images. And that's mostly because of it's a very robust index, and it's less sensitive to different sensors. So you can pretty easily compare the NDVI measured by different sensors. One of the disadvantages of the NDVI is a saturation at a high biomass. So during season with crops with a lot of canopy, there can be a saturation, especially with a lot of leaf area index with a lot of biomass. You have saturation. The second and the third one is the REIP and the NDRE. They're a bit similar to each other. They're both less sensitive than NDVI for saturation, so that's a good thing. And it's more sensitive for the amount of chlorophyll, so you can better measure the amount of chlorophyll with those two indexes. And it also says something about the end uptake and the end content of canopy of a crop. One of the disadvantages, especially for this project, is also the sensitive for sensor specification. So it's a bit harder to compare those indexes between the partners in this project, and especially because there are different sensors are used in this project. Then we have the MTCI. Also, this one can say something about the end uptake and the end content. But also the disadvantage is the same as the last one. It's sensitive to sensor specifications. So I can show you in the graph up here. This vegetation indices use the wavelength 753, which is just on the border of the red edge and the near infrared. So when you use a sensor with just a slightly different wavelength on the slope, you can see there will be a pretty big difference in reflectance. So that's why it's. Then we have the chlorophyll green. It's one of the most correlated with N contents, so that's a very good one to use within one field. But it will be very sensitive for a trial location or for different soil types, soil color. So that will be very hard to compare with other fields or with other countries, for example, in this project. But within one trial, it can be a very useful one for especially N content. Then we have the chlorophyll index red edge. Mostly it's just simplicity, the biggest advantage. It is an indicator for total chlorophyll in the canopy, but that's mostly it, not a very special index. The same disadvantage as the chlorophyll green, it's sensitive for trial location, and besides that, it's also sensitive for sensor specifications. It's very difficult to compare those with different sensors. The MCARE2, a few advantages. It's very less sensitive to different sensors, so you can compare it very easily. It's one we can use within this project pretty well. It's less sensitive to trial locations, so soil color won't be a problem, and less saturated than NDVI. One of the disadvantages is sensitive to light intensity, so different light income can cause a different index outcome. A summary of all the advantage and disadvantage, especially when you have to choose what kind of index you want to use. We try to make a summary. It's based on the experience of the partners, and also based on the scientific literature, and so we try to make it a bit easier to choose the best index for your usage, and we will probably update it when we have more results in this project. The X mean that it can be used pretty well for your purpose, and the exclamation mark just means but you can use it, but you have to be very keen on it, on your calibration of the sensor, and you have to be very careful to compare between different sensors in those indexes. So you better, maybe you can have a look later on when you have the slides of this presentation. This is the end of my presentation. We now go to the questions.
Thanks, Hans. We've now got a few minutes for questions. Can we move to the next slide? So just a reminder, if you have any questions, you can type them in your question box. We've got a couple that have come in, but we might be able to pick up others at the later question session as well. So we've got someone who was asking about the level of data processing that you need to do for the different sensors, and whether that's different between sensor type. I wonder, Guys, is that one that you could pick up?
Yes, maybe. Yeah, there is a difference between the different sensors. Each sensor has its bit of its own processing chain, but it's important that you mentioned there is a difference between multispectral and hyperspectral measurements, because for multispectral measurements we have 5 bands, 10 bands we measure. For hyperspectral data we got like 100 bands or more. So it asks another manner of processing the data. There is even a bigger difference between, for example, drone images and images of, for example, handheld sensors. Because by the drone images, we got for each plot like 10,000 pixels. So we need first to use like his data to process the image and to have one value for each plot, and then afterwards we can process it further. So according to the type of sensor you're using, you need to have a different processing chain.
Okay, thank you. Another question following on from that related to the sensors is whether the sensors themselves give you the vegetation index, or whether you have to calculate that separately. Guys, again, is that one that you could pick up?
It's also depending on the type of sensor you're using. For example, some drone programs will give almost directly a processed image, where you can see, for example, NDVI. But we at the projects, we like to have the raw data. So we want to have for each point the data of each band separately. So we process it for each band separately, and then afterwards we can calculate the vegetation indexes, because it gives us more room to change some things.
Okay, thank you. I think this is one for you, Hans. We had someone asking where you go to find out information about vegetation indices. Is there somewhere that has information on different types of indices?
There is a site, we can probably put it down in the chat. It was index databases. I will have a look.
Yes, so I think that's a site that we've used.
Yeah, it's a site, indexdatabases.de, and all the different vegetation indexes are collected there, and with different scientific research is on there. So.
Okay, thank you for that. I think we're due to time, move on to the next session now, but please keep putting your questions in the box because we might have more time at the end as well. So Guy, Hans, thank you very much. And now I'd like to invite Jean-Pierre to present the next session.
Okay, thank you very much, Lindsay. I take the microphone to present you the third presentation of this meeting about the comparison we made and we are still making on the different sensors we would like to use in the project. Why do we want to do that? In fact, the main objective of the project is to build some relation between the variable we could measure with sensors and some agronomic traits for various purposes, for technicians, for farmers, for breeders, etc., etc. And we know that if we want to make good science, we need a lot of trials, field trials and field experiments at the same time or in different years, etc. So we will be obliged, we think, to merge, to mix some various data sets from different sensors. And as my colleagues told you during the previous presentation, we know that sensors could have some strong differences concerning their technical specificities. So we need to make some comparison to be sure that it's not meaningless to merge, for example, an NDVI datasets from MicaSense sensors and from an Delphy sensors, for example. That's why we start to make a comparison process between the sensors. So this presentation will be divided in 5 points. First of all, we would like to present you what we call the sensor simulator. It's a big name, but don't worry, very easy to understand. And then I will explain the principle of the comparison we made and how it's connected with the relative sensitivity of the vegetation indexes to the sensor's characteristics. At the end, I will show some first result concerning the risk of error we could do by mixing data sets from different sensors, which is the core of our subject for this presentation. And I will conclude on the compromise between the agronomic accuracy of vegetation indices and the sensor's robustness of these indices. So the sensor simulator. The principle is very simple, in fact. In our project, we have two sensors, namely the field spec in UK and the Delphy in France, which are using spectral radiometers. And those spectral radiometers give us two hyperspectral datasets with all wavelength from 400 nanometers to 900. So we have the full spectra with 2 sensors and on 3 species: potatoes, carrot, and vining peas. And on the trials where we use these sensors, we could extract all the wavelength we want. And by doing that, we can use this wavelength, these bands, to simulate all the sensors we have in the project, because each sensor is defined by its technical specificities, namely the central wavelength position, the exact central wavelength position of each band, the width of the spectral band, which could be narrow, approximately 3 or 4 nanometers, but it could be also wide and very wide. And the third characteristic of a sensors we take into account is the shape of the spectral sensitivity. You could have a punctual shape, which means that you only consider the central wavelength of each band. You could have a gated sensitivity, which means that you consider the mean of all wavelengths of the band, and you could also have a Gaussian sensitivity to consider the whole spectra around the wavelength of the band. So those 3 characteristics are specific to each sensor. So by using that and our 2 hyperspectral datasets, we are able to calculate some virtual equivalence of each sensor. And so we can compute on the trials the simulated vegetation indices as if it could be acquired by different sensors. So to be clear, we don't use all physical sensors on each trials, but we simulate all sensors by using some hyperspectral datasets. On this slide, you can see the characteristic of some sensors we use on our project. At the bottom of the slide, it is a full spectra acquired by FieldScan and Delphy. And at the top, you can see the corresponding wavelength and bands for downgraded Delphy, which is used by Arvalis, and for the DJI multi-drone, also used by Arvalis, and an example of the MicaSense Blue and the Spectracam, which are used respectively by INNO-VEG and Delphy. So as you can see, the sensors we work with show different, strong difference considering some wavelength according to the central wavelength, but also the shape of the band around the central wavelength. So we need to compare those sensors because we could expect some strong difference regarding the absolute value of the vegetation indices calculated and measured by each sensor. The main principle of comparison is not difficult to explain. The first stage is the measurement on trials. So as I already mentioned, we use 2 sensors, the field spec or Delphy, field spec in UK and Delphy in France. And in these tools, we use the spectral radiometer. We allow us to obtain the full spectra reflectance. By using those reflectance data, we calculate the reference, which is called canonical vegetation indices. VI is for vegetation indices. So with following characteristic, we use the exact central wavelength for each band. We use a very narrow width band of 4 nanometers, meaning more or less 2 nanometers around the central wavelength. And we use a Gaussian distribution filter to simulate, to calculate the global reflectance obtained by the band. So it is our reference. Then we use a sensor simulator to create each virtual sensor, meaning a virtual MicaSense, a virtual Spectracam, etc., etc. And we calculate the vegetation indices for each virtual sensor by using its own specificity, central wavelength, bandwidth, Victor limits, etc., etc. So we have a data set for each vegetation indices and each virtual sensors. Then we compare those data sets with the reference by doing some basic statistics like correlation, etc., but also some more complicated statistics to estimate, for example, the relative standard error we could make by using sensors compared to the reference. This last information is very, very important because it's with this information we could estimate the risk we took to mix dataset from very different sensors, the risk on the final result, and the interpretation we could make of a value of a vegetation indices related to an agronomic traits like yield or nitrogen content or biomass, etc., etc. And for this first results, we use 6 trials. So 2 French trials on potatoes, 2 UK trials on carrots, and 2 UK trials on vining beans. Of course, we have more data than those 6 trials, but it was our first attempt to make this comparison. And if we need to add more data to go deeper to understand the result we obtain, we will do it, of course. Just to explain why some vegetation indices could be more or less sensitive compared to the other, I would like to show you these plots, which is a classical plots of the reflectance. This is the y-axis, according to the wavelength. This is the x-axis. You already saw this type of plots in the previous presentation. If I took the example of the vegetation indices that are using the green, the red, and the near infrared bands, you can see that they are likely to be less sensitive to the sensor's characteristic because some small variation around the central wavelength won't have any big consequences on the absolute value of the reflectance. So it's the case, for example, for NDVI, chlorophyll green, MCARI2, etc. In the other end, if you want to use some vegetation indices using the red edge band, you could have some risk because some small variation of the wavelength you measure could have strong consequences on the absolute value of the reflectance because you are in the near red edge front. And this is the case, for example, for MTCIs, chlorophyll red edge, REIP, etc. All the vegetation indices using the red edge band could be more sensitive to those sensors specificities. And to illustrate the difference between two vegetation indices, you can see on this slide some correlation graph. It's a little bit complicated to read, so I will help you. Don't worry. On the left part of the slide, this is an example of NDVI correlation between sensors. So it is a basic correlation between all sensors. And on the right part of the slide, this is exactly the same graph, but for MTCIs on the same datasets. For NDVI, the orange box show you the correlation and the value in the correlation plot of each sensors compared to the reference. As you can see, the correlation are generally very high for less sensitive vegetation indices like NDVI. So we consider that there are no need to go deeper in the comparison because we confirm that NDVI is very robust when you want to mix some different dataset from different sensors. In the other end, you can see that MTCIs, which is using the red edge band, could show some problems and could be seen more sensitive to the sensor's characteristics. So we need to go deeper by estimating the relative error we could make when we want to mix some different datasets. And this is the subject of this slide. The plot you can see on the right side of the slide is the relative standard error we calculated for each situation we measured for each sensors compared to the reference. And as you can see, the error range from 0, there is no problem, to more than 30% of error, which is very high. And we calculated those error for 3 vegetation indices using the red edge band, C red edge, MTCIs, and REIP. So approximately 9% of the situation we studied are above the 10% error limit, which is quite high. And if we consider a 5% error limit, approximately 23% of the situation are above the limit. So for vegetation indices like MTCIs or chlorophyll red edge, it could be a problem. So some work needs to be done to go deeper because it's only first result, and we need the rest of the project to understand why some situations are more problematic than others. And also we need to evaluate the impact of the error regarding the agronomic interpretation of the vegetation indices, because it's the final conclusion which is very important for us. So the story is not over, and it's just first result. So as a conclusion, I already mentioned that we need to make a compromise between the agronomic accuracy and the sensor robustness of vegetation indices. For example, on the left, in some cases, a robust vegetation indices like NDVI could be enough to address the targeted trait. This is an example of vining peas trials in UK from EADAS. And as you can see, NDVI is well correlated to the yield. So it's enough for us, and we don't need to go deeper or to choose another vegetation indices. In the other hand, on the right part of the slide, as you can see, it's a potato trial in France from Arvalis. The kinetics of NDVIs show difficulties to discriminate the treatment. The treatment in this case is cultivars of potato cultivars. And MTCIs is more able to discriminate treatment, so more interesting. but we know that MTCI is more sensitive to sensors. So the purpose of the project will be to find the best sensor variable to assess the targeted trait for various users, by considering also their sensors robustness to be able to use them in large field trials network. So it will be the main topic of the project until its end. Okay, it's the end of my presentation. I will give the microphone to Lizzie for the conclusion.
Thank you, Jean-Pierre. I just wanted to say a few words to finish, and then we've got time for a few more questions. Next slide. So past work has shown, and we've seen in this project, that vegetation indices can be used as an indicator of crop growth. Key advantages of using crop reflectance data to monitor crops are that the measurements are non-destructive and it's relatively quick and easy to collect the data. And this is particularly useful where we want to monitor crops over larger whole field or fields areas. We've seen that there are a wide range of different vegetation indices that can be calculated and used. Many sensor providers calculate and give you NDVI as standard. However, if you're using multi or hyperspectral sensors, consider looking at other vegetation indices as well. We know that other indices, particularly those using the red edge band, can be more sensitive to showing up differences in certain crop characteristics, as Jean-Pierre has just mentioned. If you're interested in looking at what other indices are available, you can look to the scientific literature or information available on online databases such as Index Database, which Hans mentioned earlier. However, we would say that it might not be useful to spend time calculating vast numbers of different vegetation indices, as many of them are highly correlated to each other. In this project, we've mentioned that we've calculated 7 different vegetation indices. These were selected based on the experience of the partners to give us a selection which include different crop reflectance bands and which have been shown previously to be correlated to particular crop parameters. Another thing I want to highlight is measurement timing. We've seen that measurement timing in terms of crop growth stage is really quite important. As expected in the work that we've done, we've seen differences in the level of correlation between vegetation indices and yield depending on when we take the measurement during the season. For example, in potatoes, measurement of the senescence dynamic can be used to estimate production traits. In onions, we've seen the highest correlations with yield just before the onion tops bend over. We'd see generally for the crops that are harvested before they senesce, the measurements made closer to the harvest date have generally had a higher correlation to yield. In vining peas, for example, we got the best correlation with yield at full flower about 2 weeks before harvest. So as part of our work in this project, and as I mentioned, we're about halfway through at the moment, we will provide information on the performance of these 7 vegetation index and impact of measurement timing for the crops that we've been looking at. This information will be published on our project website, which we've got at the bottom of the slide there, alongside general good practice recommendations for collecting and processing this sort of crop reflectance data. And we hope to have this available later this year. I'd like to just encourage you to visit the website and register. You can register on the project website to receive updates. And that means we can email you when we publish documents from the project or plan to hold any other meetings or webinars. We've now just got a little bit of time to take a couple more questions. So I'd just like to invite Jean-Pierre to put his camera back on as well. Okay, so I'm just looking at the questions that have come through. We've got one here about water content of plants. It's is there any sensor that estimates the water needs of the plant? And if yes, is it a handheld or tractor mounted sensor that can do that? Is that something you're able to pick up?
Yes, to be honest, I think that the water needs of a crop is one of the most complicated traits to estimate with the sensors. We could have some proxy using some indices connected to leaf area index and the leaf area index dynamics. But we need to couple this information with some crop model, or at least a water balance calculation, considering the soil characteristic, etc. But it's possible. There is some literature result available, and the other part of the question is about which sensors could be used to do that. I would say that every sensor which could hold an RGB camera or multispectral camera could give some information to calculate some indices connected to the water needs, but it's pretty hard to interpret without a water balance calculation, I think.
Okay, thank you. We've had another question about satellite data and whether we can comment on how well satellite data would compare to some of the sensors that we are using.
We have not included some satellite data in our project, but data from satellite could be useful to have access to some sensors variables, and it could be very useful if you want to conduct some large field trials. The main limits of the sensors data from satellite is that you don't control exactly the date of the measurement, because you need to choose the images available in images when the satellite fly over the field, and you cannot control exactly the date, the exact day or the time of the day when the satellite will pass. But anyway, satellite is a good way to have some sensors data. So I think the general principle and the general result we will produce on our project could be useful to interpret vegetation indices or the sensors variables acquired by satellite.
Okay, thank you. There's just one more question, although it might be a bit tricky to answer for us in our project. We've got someone saying all trials are regarding line sowing crops. Can we use sensors indices for mixed or intercropping? I don't know whether, Jean-Pierre, you have any comments on that?
Yes, it's a tricky question because in our project we only address some pure crop without any mix of cover crop or mix of different species, etc., etc. But I agree that it's a very important question for now, because complex cover is one of the solutions to overcome some big problem of nutrition, etc., etc. But it's quite a challenge for sensors, because if we want to be very accurate, we need to discriminate the different type of covers on the same images, and it could be difficult. So we need a very complicated processing chain to discriminate each pixels of, for example, wheat and legume, for example. So it's possible, but it's not available yet.
Yep.
Sorry.
Okay, thank you very much. We're coming towards the end of our slot now, so I'm going to wrap up the questions and pass back to Jean-Pierre to close the webinar.
Okay, so the last slide of our webinar is about an announcement. The INNO-VEG project is a scientific project. We will produce some very valuable results for everybody, but it's also a cooperative project. because we want to build some links between all the users of sensors, between the technology industry and companies, the research centers and organizations, and also between farmers. We could use those sensors to make some experiment in their farms. So the main objective is to share, to realize together the value of crop sensing technology in the research process. So to do that, we set up a cross-border innovation network between the 4 countries inside the project. So you can join this network for free by registering on the INNO-VEG website. So do not hesitate. As a member, you could add a profile on the website and share some information on your situation or on the services you can provide, or some idea you want to share. So do not hesitate. And this network is dedicated to all sensors users for agronomic purposes. So it's up to you to register and to join us to make progressing together the sensors scientific question. Okay, that's it's finished for today. I just have to say thank you for joining. It was an experience for us because it was our first big virtual event for the project. So really, I would like to thank you in behalf of all the partners to join the meeting. It's a real pleasure to share our result. And do not hesitate to follow the project on our website, and we will probably organize some other webinar during next year and the year after to deliver our result. And we hope that we will be able to deliver those results in real life when the situation will allow us to organize conference and real meeting. Thank you, take care, and rendezvous in the future for some new result from our project. Goodbye.